In this video, we're going to look at two more topological properties for sets in a metric space. We will see what a connected set is, as well as what a path-connected set is. These are different notions. There are other types of connectivity, like simple connectedness, that we won't talk about in this video. So here's an outline of what we're going to do. The first thing I'm going to show you is what the definition of a connected set is, and I'll provide you with a quick example of a set which is actually not connected. Then we will look at a set which is connected, so we will prove that the closed bounded interval on the real number line from, say, A to B is a connected set. After that, we will talk about the definition of a path-connected set, and I actually think that this is an easier one to picture. So we'll look at a few examples. I want to mention the idea of parameterization and reparameterization, and then we will prove a result that if A is path-connected, then A is connected. So the definition I think is easier, that of path connectivity, is actually a stronger condition. Then we'll wrap everything up with a quick look at a famous curve called the Topologist sine curve. There are different versions of this, so the one I will show you is the closed Topologist sine curve. All right, so first let's define connected sets. If we have a subset called A of a metric space, we say two open sets U and V separate A if four conditions hold. The first is that A is covered by the union of U and V. In other words, every element in A can be found in either U or V. Conditions 2 and 3 go together, and those are that while U and V together are covering A, both are contributing. So it's not the case that U entirely covers A and V is off disjoint from A. Instead, both contribute. And then symbolically, we can represent that by saying that the intersection of A with either set is non-empty. And then the fourth one is important. This really gives the idea of separating A. And that is that U and V are disjoint over A. So no element in A is found in both U and V. Symbolically, we could say that the intersection of U and V in A, or in other words, U intersect V intersect A, is the empty set. So you can think of U and V as forming a disjoint open cover of A with two sets. And here my use of the word disjoint is like disjoint relative to A. That's the condition in the fourth statement. Okay, this definition might surprise you because I promised that I was going to define the idea of a connected set, and here I'm defining the idea of a set which can be separated. In fact, these notions are basically opposite. So if U and V separate A, we say that A is disconnected. If this cannot happen, so if you cannot find such sets U and V, then A is connected. So connected sets are defined by what they are not. It's kind of like how we have a definition for rational numbers. They can be written as ratios of integers. And then we say a number is irrational if it is not that. So this is similar. We say that A is connected if it is not something else. For that reason, I think when you first learn this, it's easier to work with the idea of a disconnected set. So for our first example, let's show that the set of rational numbers as a subset of the Euclidean real line is disconnected. If you would like to, you can pause for a few moments and see if you can come up with two open sets U and V which match this description. So together, U and V need to cover every rational number. Both of them have to cover at least one rational number, but no rational number can be found in both. Okay, maybe you got such sets, but if you need a hint, think about two open intervals covering almost the entire real number line. Okay, here's my solution. Let the open set U be the open interval from negative infinity up to the irrational number e. And then let V go from e to infinity. Let's check the four conditions. Every rational number smaller than e is covered by U, whereas every rational number larger than e is covered by V. Therefore, both contribute to the cover. So 0 is covered by U, whereas 10 is covered by V. And they don't overlap at all, so the intersection of U and V is empty. So together, these two open intervals separate the rational numbers, so we can conclude that the rational numbers is a disconnected set. So I think the approach to showing that a set is disconnected is easier in some ways because you just have to come up with a pairing of U and V which work, like in this example. However, if you want to show that a set is connected using the definition, you have to show that no such pairing could exist. To me, that seems harder, but let's look at an example. So let's prove that a closed bounded interval from A to B is connected. Proof strategy here. Often if we want to show that a definition is not being met, in this case the definition of being disconnected, you assume that it is being met and set up a contradiction. So for the sake of contradiction, suppose that the interval from A to B is disconnected. In other words, I can find open sets U and V which separate the interval. What that means is that every element in this closed interval is found in either U or V, so without loss of generality, let's suppose that B, the right endpoint of the interval, is in V. Nothing to the right of B really matters, if you will, so one thing I'm going to do is redefine U if necessary to be U intersect the open interval from negative infinity to B. This new version of U is still an open set because it's the intersection of two open sets. And everything between A and B which was covered by U will still be covered by U. Basically, I just want to throw away everything to the right of the interval. So this new version of U together with V still separate the closed bounded interval from A to B, but what I can now say is that B is officially an upper bound of U. Since U is bounded above by B, by the supremum property it has a least upper bound, so let X be the supremum of U. So I know that X is, if anything, to the left of B, but it can't also be to the left of A because if it were, the entire interval from A to B would be covered by V, contradicting that U and V separate this interval. Therefore, X has to be in the closed bounded interval from A to B, and I'm going to picture it kind of between the two endpoints. Okay, so let's pause for a moment. We have the closed bounded interval from A to B. We are saying now that there's an element X somewhere in this interval which is the least upper bound of the set U. So I can imagine everything to the right of X as being covered by V. The question is, since X belongs to the interval, which of the two sets, U or V, does X belong to? Let's do this by cases. For the first case, suppose X belongs to U. Since U is an open set, X is an interior point, we can find some radius epsilon greater than 0, so that the epsilon neighborhood around X, you can write that as X minus epsilon through X plus epsilon, is a subset of U. Think about that for a moment and compare it to the diagram at the top. If this epsilon neighborhood around X was a subset of U, what's wrong with our picture? Well, what's wrong with the picture is that that right side of the interval is in U, suggesting that that right half of the interval can't also be covered by V, and also X is to the left of elements in U, so it's not an upper bound of U. This allows us to rule out the first case. It cannot be that X is in U. Moving on to the second case, consider X in V. Once again, since V is open, there exists a neighborhood around X which would be situated inside of the open set V. Pause and look at the picture. Now what's wrong? In this situation, X is still an upper bound of U, but there are other upper bounds of U to the left. So that means that there are upper bounds of U which are smaller than X, so X is not the supremum of U. So now we're saying there's some point X which belongs to this set, but which cannot belong to either U or V. That contradicts that U and V together cover the set. Therefore, the closed bounded interval from A to B cannot be separated and must be connected. I hope you enjoyed this look at how to prove a set is connected through contradiction. Let's move on now to a different type of connectivity that I think is easier to understand. So this is the notion of a path-connected set in a metric space. To define what it means to say that a set is path-connected, we first need to define the notion of a continuous path. A continuous path is going to be a function of a real number, so that's why I have real numbers a and b here. And we say that a continuous path from a point x in the metric space to another point y is a continuous function from the closed-bounded interval ab to the metric space, so that phi of a is x and phi of b is y. So you can think of the domain as some interval of time, and your continuous path is like a parametrized curve from x to y. Therefore, our notion of a continuous path joining x and y is like saying there's a way to trace in the metric space from x to y without picking up your pencil. Here, a and b are finite numbers, so that we're saying over some finite amount of time you can go from x to y. Then we say that the path lies in a subset A of the metric space if phi maps the entire time interval from A to B into A. So just like in this picture, the path literally lives in A. The image of phi is contained in the set A. This leads to our definition of a path-connected set. This set A is path-connected if every 2 points in A can be joined by a continuous path which lies in A. This example I have over to the right is a path-connected set. You can imagine taking any 2 points from this gray cloud and tracing a path from one to the other without leaving the set or picking up your pencil. I think that this version of connectivity is the easier one to understand. You are probably picturing items in the real world as being connected if you can get from one to the other, and this idea of getting from one to the other is like following a path. For example, before the Panama Canal was constructed, you could say that North and South America formed a path-connected set, but now you can't say that. So in a way which is very easy for you to immediately visualize, this set B is not path-connected because there's no way for me to travel from X on the left to Y on the right without leaving B. I want to make a few more remarks about path-connected sets. First, let's just look at some famous examples. I said you could think of this continuous path like a parametrized curve, and hopefully you've seen these examples before and they'll remind you of how to parametrize paths from one point to another. So if I define the function phi as a map from the closed bounded interval 0 pi to the xy plane, as the function phi of t equals cosine of t sine of t, then that's a parametrized path that follows the upper semicircle of radius 1, connecting the point 1, 0 to -1, 0. There are, of course, other ways to connect those 2 points, and in particular, my second example is the straight line segment parameterization. If you want to connect any 2 points in Euclidean space with a line segment, here's a formulaic way to do it. Here, the domain for the parameter is the unit interval from 0 to 1, and we say that phi of t is 1 minus t times the point where you start plus t times the point where you finish. If we're moving from p to q, that would look like 1 minus t times p plus t times q. It's a fun exercise to check that this makes sense. So plug in t equals 0, and you wipe out q, and you're left with 1 times p. So at time 0, we are at p. On the other hand, when t equals 1, we wipe out p, and we're on q. So phi of 1 lands on q. And then for any time value between 0 and 1, you have some amount of p and some amount of q, you're between the two. And you could show with some algebra or calculus that this in fact follows a straight line path. Notice in my second example, the time domain is unit length, and you can actually always reparametrize such a path to have that property. So if phi is a continuous path satisfying that phi of a is x and phi of b is y, I can essentially shift my time domain from AB to 0, 1 in this manner. What I'm going to do is create a new path called psi, following my second example up above. So in detail, psi is a map from 0, 1 to AB defined as psi of t equals 1 minus t times a plus t times b. Again, that's like the second example moving me from A to B. Now if we compose the two, we will start in 0, 1 and get mapped continuously to AB and then get mapped continuously to M, with the property that this composition, phi of psi, is a continuous path satisfying phi of 0 is x and phi of 1 is y. So this is a reparametrization of my original path so that the time duration goes from t equals 0 to t equals 1. A few minutes ago, I said that it can be difficult to show that a set is connected using the definition, but actually our next theorem gives you another way to show that a set is connected. So the theorem we are about to prove is that if a set is path connected, then it is connected. Therefore, if you prove that a set is path connected, you actually prove two things, that it's path connected and also connected. The converse, as we will see with our concluding example, is not true. A set may be connected but not path connected. Once again, like we did before, To prove that A is connected, we are actually going to proceed indirectly because I have an actual definition for what it is to say that A is not connected. So for the sake of contradiction, suppose that A is path connected but not connected. Then there exist open sets U and V so that those four properties hold. Let's revisit them. The first is that A is covered by U and V, and both contribute to the cover. So A intersect U is non-empty and A intersect V is also non-empty. And then importantly, they do not share any points in A. So every point in A is covered by either U or V, but no point is covered by both. Let's bring in our hypothesis that A is path connected. Since we know that A intersect U is non-empty and A intersect V is non-empty, we can choose a point in both of those intersections. In particular, choose X to be in A intersect U and Y to be in A intersect V. If we're assuming that A is path connected, then there's a continuous map phi from, say, AB to A, which takes us from X to Y. But the image of phi is a subset of A. So in particular, the image of phi must be covered by U and V. But I know that X is covered by U and Y is covered by V, which tells me that the image of phi intersect U is non-empty and also the image of phi intersect V is non-empty. And again, since the image of phi is a subset of A, no point in phi can be covered by both U and V, because that would correspond to a point in A being covered by both U and V, and we know that's not possible. So if you look at these four remarks that we've just made about the image of phi, we're saying that the image of phi is disconnected. However, and I'm about to cite a later result that does not depend on this discussion at all, a continuous function on a connected domain has a connected image. Again, we will prove that. We've already shown in this video that the domain from A to B is connected. Therefore, since phi is continuous, it should be the case that the image of phi is connected. That contradicts the remarks that we made above about the image of phi. Therefore, it cannot be the case that we could separate A. So if A is path connected, then A must also be connected. Okay, we've seen a lot of definitions and results in this video. Let's wrap up with a famous example. So imagine that we are working in R2, and I'm going to write the set that we're interested in as the union of two other sets. So let A be a segment on the y-axis going from -1 to 1, as I've just pictured here. And let B be the graph of the function y equals sine of 1 over x for positive values of x. Now you can take a moment to visualize what the function y equals sine of 1 over x looks like. What I like to imagine it doing as inverting the sine waves and clustering them up. If you think about it, from x equals 1 onwards, the angles that we're plugging into the sine function just decay from 1 radian down to 0. So you don't get any oscillations beyond x equals 1. But as x decreases down to 0, 1 over x is going to run us through infinitely many angles. In fact, if you just imagine a family of x values decreasing to 0 of the form 1 over pi, 1 over 2 pi, 1 over 3 pi, 1 over 4 pi, you realize that we're going to rotate around and around the unit circle. So our sine wave will oscillate infinitely many times with increasing frequency as we approach the y-axis from the right. Okay, put these two sets together. Does this union form a path-connected set? And what about a connected set? I'm going to ask them in that order. Experiment with these ideas for a few minutes, and then when you're ready, continue the video and I will take you through the answers. The answer to the first question is no. The image that we are looking at is not a path-connected set. Let me give you two ways to think about that answer. Both will be based on a choice of points. So let x be that point, say, all the way on the right, and let y be the origin. X belongs to the set B, and Y belongs to the set A on the y-axis. If we are going to trace out a path from X to Y that stays in the set, it's going to have to follow the sine curve because it's going to stay in B. Now, my first explanation is just that these sine waves approach the y-axis asymptotically. So there's no finite domain of time, which is going to allow me to suddenly land on the y-axis. The fact that these sine waves approach the y-axis is really like a limiting behavior. Okay, so that's one explanation, just that you can't get from the sine wave to the y-axis. They don't actually touch with any sort of finite time. My second explanation is just going to explore that with a little bit more detail. Imagine I have a parametrized curve. This parameterization is going to pass through all x values from 1 down to 0, and we are going to pass through all of the points on the sine curve. So in particular, identify two sequence of parameter values which map onto that sine curve as follows. So one sequence of time values I'll call c sub n, and suppose that when we plug that sequence of time values into our continuous path, it sends us to the peaks, which I've tried to add to the graph. So in particular, it sends us to all of the places where the y value is 1. This is forming a sequence along our sine wave which must converge to 0, 1 on the y-axis. On the other hand, I can design a different sequence of time values which map us down to the low points where sine is -1. And for that infinite sequence of parameter values, the corresponding outputs are converging to 0, -1. So it's like I have two sequences of time values which are sending us to different places. Therefore, there cannot be a continuous map which is going to take us from that point x to the origin. Okay, I hope you enjoyed at least one of those two explanations, that this set A union B is not path connected. On the other hand, it is connected. Here's how I would like to prove that for you. Imagine that I try to separate the union of A and B with two open sets U and V. Both A and B are individually path connected. It's not too hard to see that for either one. Therefore, by the theorem that we proved, both of them are connected, which means you can't separate A and you can't separate B. Well, since I can't separate A, I'm going to put A entirely in one of the open sets, call it U. And likewise, since I can't separate B, let's put B entirely inside of V. Let's think about what we can contradict. Together, U and V are covering the union. Both are contributing to the cover. So I need to prove that there's a point which is being covered twice by both U and V. I think the easiest point to work with here is the origin. Notice that since the origin belongs to A, it's being covered by U. And since U is an open set, there's some disk around the origin, some open neighborhood of the origin, which stays entirely inside of U. In fact, I can give that a prescriptive form. It's, say, an open disk of some radius epsilon. If you imagine what that's going to look like, it's an open disk around the origin, and my sine wave is going to start oscillating inside of the disk. We just need to verify that that happens. So choose some natural number large enough so that 1 over 2 pi times that number is smaller than epsilon. Then the point x equals 1 over 2 pi n, sine of 2 pi n, maps to the point 1 over 2 pi n, 0 on the x-axis. Since that x-coordinate is between 0 and epsilon, that point that we map to on our sine wave belongs to D and is therefore covered by U. However, it's also part of the sine wave, so it belongs to B, which is being covered by V. Therefore, this point in that disk is being covered by both U and V. Therefore, this topologist sine curve cannot be separated. So it is connected even though it is not path connected. All right, that wraps up this look at connected and path connected sets. Thank you for your attention.